A CPU fetches an instruction, decodes it, and executes it. It has no concept of intent, and it does not distinguish between a legitimate application and malicious shellcode. By blindly executing whatever is loaded into memory, the operating system becomes an accomplice to its own compromise. Evasion is not a matter of breaking the rules of a system. Instead, it relies on the strict application of the operating system's native architecture against itself. This environment represents the bedrock of system execution. To understand how modern infections operate, we have to strip away high-level abstractions and examine the raw assembly layer. At this microscopic level, every operation is predictable and atomic, a series of memory allocations, thread manipulations, and API calls. Malware hides by blending into these billions of operations. A malicious memory allocation uses the same native functions as a web browser or a system service, masking the threat through sheer volume. Because these actions are mechanically identical to legitimate ones, standard file scanning is frequently ineffective. True visibility requires deep forensic telemetry that tracks execution at the raw byte level. That byte-level analysis requires understanding the underlying hardware rules, which shifted when Windows moved from 32-bit x86 architecture to 64-bit. This transition redefined how the processor handles function arguments. Under the Microsoft x64 calling convention, the first 4 arguments load directly into hardware registers: RCX, RDX, R8, and R9. Simultaneously, the caller reserves 32 bytes of shadow space on the stack, providing an area for the receiving function to spill register data. Analysts use these rules to map a program's logic into a control flow graph, or CFG, which connects discrete chunks of execution called basic blocks. A basic block is a maximal sequence of instructions where execution enters only at the first instruction and exits only at the last, via a jump, branch, or return. Malware authors attempt to break these graphs using opaque predicates, comparisons that always evaluate to a known state, but appear as branches to analysis tools. For example, the instruction XR EAX EAX, followed by CMP EAX EAX, will always result in the 0 flag being set. While the outcome is mathematically fixed, a disassembler will still map a conditional branch for both a true and a false outcome. By forcing the disassembler to draw these dead edges, the malware shatters the CFG. This makes the true logic of the binary difficult to follow through static analysis alone. Beyond raw assembly, malware exploits how code is packaged in dynamic link libraries. When an application needs a function, the Windows loader follows a specific tiered search order to locate the required DLL. Attackers exploit this sequence through DLL sideloading. By placing a malicious DLL in a directory searched before the legitimate one, the attacker ensures the operating system loads the weaponized code instead. Because the application itself requests the load, this technique bypasses the safeguards introduced with safe DLL search mode. While sideloading relies on files on disk, code injection allows malware to operate entirely in memory. The standard injection pipeline uses open process, virtual ALEC-X, and write process memory to force code into a running process, though these APIs are heavily monitored by security products. Reflective DLL injection provides a more stealthy alternative. It avoids the Windows loader entirely, meaning the malicious code never passes through the standard load library API. In this method, the DLL contains its own custom loader. Once written to memory, it manually resolves its own imports and performs relocations without interacting with the operating system's management functions. Because the standard loader is bypassed, the reflective DLL does not appear in the process environment block module list, effectively hiding it from many memory scanners. Process hollowing takes this further by violently replacing the executable image of a legitimate process with malicious code. This allows the malware to operate under the identity of a trusted Windows binary. First, the malware spawns a legitimate process, such as svchost.exe, in a suspended state, using the createProcess API. While the process is frozen, the nt_unmap_view_of_section call unmaps the legitimate code section from the target's address space. The attacker then allocates new memory, writes the payload into the shell, sets the thread context, and calls resume thread. The process appears legitimate in task managers, but its memory contains the attacker's code. An alternative timing method is asynchronous procedure call, or APC, injection. For an APC to execute, the target thread must be in an alertable wait state, a specific condition where the thread is idle and ready to process queued tasks. Standard APC injection is often unreliable because it depends on the thread state. The early bird variant solves this by targeting a newly created process. By queuing the APC while the process is still suspended, the payload executes before security products can install their own monitoring hooks, allowing the malware to gain control before it is being watched. Once running, malware must often hide its presence from the user. It achieves this through API hooking, intercepting and redirecting function calls between the application and the operating system. IAT hooking is a straightforward method that modifies the import address table. By overwriting an entry, the malware ensures that any call to a specific function is redirected to a malicious address in memory. A more complex approach is inline trampoline hooking, which modifies the code of the target function itself. This technique overwrites the first few bytes of a function with a JMP instruction. When called, execution is diverted to the malware's custom handler. The handler uses a trampoline, a code stub with the original bytes, to execute the legitimate function and return safely. By intercepting these calls, the malware can filter the results of functions that query the system, effectively removing its own files and network connections from directory listings and task managers. Evasion techniques can also leverage the deep, undocumented states of the Windows kernel. The Heaven's Gate technique allows a 32-bit process to escape its emulated environment on a 64-bit system, which can bypass many 32-bit debuggers and analysis tools. By executing a FAR JMP instruction, the malware switches the CPU to 64-bit long mode. This allows it to issue native 64-bit system calls that are invisible to the 32-bit subsystem. Process doppelganging focuses on exploiting the file system rather than the memory space. This technique abuses the NTFS delete pending state. It maps a malicious payload into memory as a file, then rolls back the transaction before the file is ever formally written to the disk. Because the transaction is rolled back, no malicious file remains for an antivirus scanner to find, yet the code executes successfully in memory. These methods culminate in living-off-the-land attacks, where the adversary uses the system's own trusted binaries against it. Microsoft-signed utilities like certutil.exe or mshta.exe are abused to download and execute code. Since these are legitimate system components, their use often bypasses application whitelisting and traditional security controls. Persistence can be achieved through COM hijacking, which manipulates the registry to redirect legitimate system requests into malicious ones, requiring no new executables on the disk. Countering these threats requires moving past simple file scans. Analysts must use deep system telemetry, such as Sysmon Event ID 1, to track suspicious process creation hierarchies. Memory forensics is often the only way to confirm these infections post-execution. Tools like Volatility allow analysts to scan RAM for private executable memory regions. These are areas of memory that contain code but have no corresponding file on the disk, the hallmark of an injected payload. Ultimately, identifying these subsurface behaviors depends on monitoring the architectural deviations that occur when a trusted process is subverted. By tracking the misuse of low-level system calls in memory regions, defenders can expose the hidden logic that signature-based defenses miss.